Okay. Ladies and gentlemen, it's a great honor to invite Professor Tongyi Zhang to give a Hong Kong IAS Distinguished Lecture Series. The topic is Materials-GPT and Domain Knowledge Guided Machine Learning. Professor Zhang, I assume most people know him already. He got so many titles and awards. Here I will only mention a few major ones. He's a member of Chinese Academy of Science, academician. He's a founding director of a Materials Genome Engineering Division in Genome Institute in Shanghai University. And he's also founding director of a Materials Genome Engineering Division in Chinese MIS. He's also he received many awards. This one, the 2018 Prize for Scientific and Technology Progress from HKIAS Foundation. The second prize of 2007 and the 1987 State Natural Science Award in China. And got so many, I'll just stop here and let Professor Zhang to give us the lecture. Professor Zhang.
Okay. Good morning. It's very, very happy to be here again. Actually, it's many years ago, CT invited me to give this IAS seminar. It's many years ago. Okay, I'm very happy to see so many all the friends, and thank you for Yuntian and Xie Li for their invitation. And you say these two, okay, 是我的前辈啊 okay, thank you for your time. Okay, and also. We have my former colleague at Hong Kong UST. Now he is the dean, okay, now at the CTU in this university. Very, very happy. I'm sure what I'm doing recently, okay, with you. The presentation topic, I call it Materials and Mechanics GPT, and Domain Knowledge Guided Machine Learning. So why I put it not only materials and mechanics. Well, I was trained in materials science and engineering. But when I do a lot of theoretical fundamental research, especially at the Hong Kong USD, so I use a lot of mechanics. You have to handle when you handle you handle dislocation theories, phase transformation theory. You have to face those mechanical properties and mechanics, okay? So that's why I do a lot of mechanics. So now I am also working in the two areas, okay, to field. So on purpose I did not put it there. Okay, I know how to do it. Okay, I will say my working experience. Okay. I used to work at the Hong Kong USD for many, many years. When I decided to return to the mainland China, then Professor Xu Guangdi, okay, he was the former mayor, okay, of Shanghai city. He invited me, asked me to join the Shanghai University. I talked to this news to CT. CT said, "Oh, Guangdi invited you. You have to go." Okay, so he asked me to go. So that's he make those. So I joined the Shanghai University. Developed. I will show you what developer is working on Materials Genome Initiative. So I built up this we call MGI. Now we change it, Materials Genome Institute. We still call MGI. Okay. So this MGI actually was announced by the former president, US President Obama, in 2011. Okay. So now, in 3 years later, in 2014, the US put there, they call that is for the materials genome, what they should do, they call strategy plan. Then in 10 years, in 2021, they still talk about the strategy plan. They summarize. And also, they give what is the future should do, okay? So that's, I'm working on that, okay, for so many years. And at that time, from, say, 2011, I began to study machine learning, okay? That's why I learn a lot of AI, and also I published the further book. I send you your one, okay, copy. Okay, it's here, okay, we send you another one, okay. So we have, working on this. Now in 2021, the US NSF, they also summarized. Okay, they invited a lot of experts and famous people. They summarize what's going on about MGI. Then they give a report. The report is called DMEREF. What that means? That means, okay, it's here, okay. Design materials to revolutionize and engineer our future. So materials is very, very important. Okay? So that's the way I emphasize, okay? So then they also review the current status of MGI over the world. When they talk about, they say the MGI development in China, I'm very happy to say that. They only majorly talk about this Shanghai University. Okay, that is the institute that developed by me, okay. Actually, Professor Zhang, so he's do all the other administrative issues. Then I can focus myself on machine learning, okay, on AI. That's why I can share my experience with you, okay, about what's going on. So now materials, to materials people, I call it materials informatics. To mechanics people, community, I call it mechanics informatics. They're basically the same, okay. So in the original MGI in the US, they call this one, this part, they call it computational tools. But in China, because we don't have this high throughput computation software, so therefore we emphasize as high throughput computation. The purpose is to try, to promote, to develop this is a high throughput computation software for algorithm. So in experimental originally in the US, they talk about these experimental tools. So now, in China, we don't have this high throughput experiment. So therefore, we put high throughput there. Then the third one is the same. This is the original one. So this one is the Chinese Academy of Engineers. We submit a report to the central government. So originally, everything is writing in Chinese. Okay. In 2015, I organized one of those MGI committee. So where I invited a lot of famous professors from the US and also famous professors in China. So for that, originally we let Xu Kuangdi will make a presentation. Then I talked to his secretary. Because we have a foreigner, so I translate her. That is actually translated for Kuangdi. Okay. So then I translate her in English. That is, but the basic, the meaning, more or less the same. Okay. So what I mean is the materials of mechanics informatics just employs those AI, machine learning technology. Okay, to that technology, to materials or mechanics science engineer, to accelerate the materials mechanics products and manufacturing innovation. We call the whole chain, okay, from materials, create a new material, design new material, to industry application. We call it the whole chain. Okay, we have to do that. Okay. Now I talk to you say materials people. I think it's mostly you are, or maybe some mechanics people. But I talk to you. You have your original. You have your a lot of you say tools. Okay, a lot of you say theories and the method. But all your methods are very, very good, excellent. Okay, that's I put here. Here I have put MD simulation, phase field, thermodynamics, dislocations, file element, and so on. Okay, you have a lot of things. Okay, but I strongly suggest you to learning a new tool. It's just a tool. Okay, keep that in mind. The new tool is AI. It's machine learning. Okay, I urge you all to equip yourself a new tool, AI, machine learning. Okay, so keep that in mind. So I put there, strengths domain knowledge, no matter what you are doing. Okay, strengthening your domain knowledge and take a new tool, make you success. Okay, you have to do that. So now, just recently, this year, okay, this year we have ChatGPT. Everybody knows, okay, ChatGPT. But ChatGPT, I changed the chat. And also I'm not focused on the natural language processing. I focus on materials. To make materials, people focus on materials. To mechanics, people talk about mechanics. To Guohua, I emphasize on battery. Okay, so I have some students utilize AI to do battery. Okay, battery research. So, but I like those. They say the GPT. I like those three words. G means generative. You have something creative. You have something new. Okay, that's what we talk about the generative. The pre-trained. Okay, I like that. When you was a child, your mother, your parents pre-train you. Then you go to school, then the school teachers and all professors train you. Once you become, a graduate students, you become, a graduate students, levels, you are trained. Okay. At my levels, I still train myself. I have to train. I try to reach those two levels. Okay, they are pre-trained. The whole life pre-trained is a whole life learning process. You have to learn. Once you trained, you know everything. Okay, if you don't train, then you don't know that. Transformer is one of the algorithms in AI. The title of this algorithm for this article, okay, they call it attention is all you need. Attention. Okay, I have to pay more attention to all electron package, microelectronics. Okay, attention, high temperature. Okay, alloys. Okay, intermetallics. Okay, I have to pay attention. Attention is all you need. So, how you can put attention? You need your domain knowledge. Okay, you need a very strong domain knowledge. Okay, I emphasize that again. Now some people propose that they call AI for science. So I talked to those people. I said, oh, AI for science is not just a software. AI for science have two parts. We talk about the science and technology. We have two parts. So first, I emphasize that. I said that you have to use the domain knowledge guide the AI, and guide the experiment and the computation. How you do that before you just use your brain, okay? Your own brain to guide. Now I ask you to use your domain knowledge, but I have all guided AI. And they have two parts. One part is a developer of materials informatics, demands for materials AI lab. You have to AI lab. AI lab is not automatic, it's a lab. If everything automatic, then in the industry they are doing that well. I'm wasting a lot of famous those industry. So for example, Boss here, I have seen them many times, and also Style, okay, for battery. They are the very, very large manufacturer, very, very few people. Everything is automatic. But here, I emphasize is AI. They have to think what's going on for our university, for our research institute. If something is uncertain, okay, we have to consider. We have your in loop to build in this feedback to know what's the next step, to replace your brain, but your brain actually plus computer, put them together. Okay, that is my purpose. And also, they have another part, very, very important, that we know that computation. Okay, I mentioned that is for materials research, you have principle is a calculation. Okay, you are expert, principal calculation, I know that. And also, we have a molecular dynamics simulation, we have a phase field simulation, we have a finite element, so on, so many different numerical calculations. Okay, so you have to put AI there. How to improve your computation? Okay, that's very, very important. So I take that, I call it experiment parts as hard parts. Computation parts, I call it soft parts. In my mind, both hard and soft are foundations to our materials science engineering, actually to nature science. Okay, so we cannot just say, so AI for science is purely computation. They should say including experiment. Okay, very, very important. So both they should be very strong and solid. That's my personal opinion. Okay. Now, give you an example. Okay. So this one, we show. Okay. The first paper is published in 2020 in Nature. They call it a mobile robotic chemistry. Okay. And after I read that, I try to build up the same thing lab. It may not for chemistry, maybe for metals, for high entropy errors, doesn't matter. Okay. So maybe for heterogeneous errors. Okay. So for that, I need some money. Okay. So I'm getting that money. Okay. So that's why, maybe for battery. Okay. So now I'll try. It's hard to realize my dream, get this AI lab. So what can I do? I try to found Hong Kong, USD, Guangzhou. Okay, I joined them because those leaders, president, vice president, all my former colleagues. They talk to me. They say, "Oh, Tongyi, you have to come back to support this new university." So I agree. That's what you ask me now. Now I have to take care of Shanghai University and also Hong Kong USD Guangzhou. Okay, so I have to take care. So now there are new university. New university has an advantage. They have money. Okay, they have a lab space. I know it's here, lab space. So 10, small. So I organize a lot of young assistant professors, majorly they are assistant professors, work together. They have their own background, different background. But we are the first group, okay, as one example. The materials we use the solar cell. We want to develop this AI lab from materials design to solar cell device. The whole, the entire things. We're still working on very, very hard. Okay, okay. So there, just to show if you ask your students to do that, Okay, the student is doing, even though they are well-trained PhD student, so they are doing very, very slow. And also, the data get them have a greater scatter, especially for battery. Okay, Guohua, I know that. Okay, I have many students working on battery. Okay, so you just reported the best results. Those results are not good. You never mention it. The students never mention it. So we have to do that. We usually say that is initial, very, very initial results. We operate by a robotic system. Okay, then we can operate that. Okay, now we still improve. You still working on it. Okay, still working on it. Now this I just added this PPT. Okay, for you, for you. Okay, so talk about its metals. Okay, so you have metals. So I think the CT get some, you get some a patent. They also transfer get a lot of money. Okay, for you put a copper on the steel. Okay, so that's same things like that. Now you have materials. Your materials, you can determine the materials by composition. You fabricate that. This I talk about is a thermal treatment. Okay, the heat treatment. You have a preliminary solution, then you do an agent. At a high temperature, you try to get them into a single phase, homogenize them. Then you cool it down. Then you heat them to a low temperature. Then, like this, is a precipitation occurs. Then form the nanoparticles. Okay, those is a nanoparticle. Their size, geometry, configuration play very, very important role in mechanical properties of materials. Okay, that is something in Yuntian. You are still working on that. Okay, we never finish. So there, you can see you typically in aluminum alloy. You talk about aluminum alloy. In aluminum alloy, they have a 3-stage heat treatment that goes through the 3 times. So after each of them, so you can do various characterization. But unfortunately, from the data we found from the literature, we did not get the characterization, microstructure data. If you have, we can do it. But we found that they are mechanical testing. Finally, they will do a uniaxial tensile testing to determine the ultimate tensile strength, we call UTIS. Then also, ductility use the elongation. That's 2 very, very important property. Everybody is working on this, we know that. So now we can do that. Then, so here is an AI model I built up based on your simulation. In the AI lab, any stage I can go back to check. I can go back, especially if you have the characterization results. Any step I can go back. Can ask, oh, you want to improve your performance, your materials. You want to change the composition, or you want to change the thermal mechanical treatment condition. You can put everything there. Okay, you can do. But that depends on the data. So we are build up this data. So now from this data, I get that the AI model give those results. Okay. Okay. So we have not to do anything to the data. Okay. We just use this available data. We did this. Okay. So now, as a material scientist, I talk about my understanding about AI. Okay. So the AI, the basic have 2 methodology or 2 approaches. One is called statistical learning. So those in the classical AI machine learning, basically is a statistical learning. Okay. But now we are talking about deeper learning. So I call it artificial neural network. So for that, what's going on, nobody knows. Okay. So I maybe use the word, even though the mathematicians don't know what's going on. they just partially use some, in some step use static learning, use the probability. But as a whole, okay, the artificial. So those AI people just think our brain just think is that. So that's why they call artificial neural network. They call it artificial neural network. So now, deep learning at the current stage, I use the famous word from Deng Xiaoping. 黑猫白猫抓着耗子就是好猫。okay, that's it. Now they develop so fast. So there, as one example I put it there, there's a cycle gun. Cycle gun, they are able, gun, I'm not giving more detail, okay. A gun is able to convert a photograph to various style of painting. If you like, some classical, some famous painter's style, okay, you can use that. You have a picture, use your iPhone, you take a picture, then you can convert it, okay? So that's no problem. So now, from us, we are trying to find knowledge. What is knowledge? In my mind, everything you have to write in mathematical equation. Okay, not is if you can use a math, okay, use an equation formula to describe it, that's indicated you fully understand it. Otherwise, just partially understand. Okay, so we need this. So at the beginning, I don't pay too much attention to deep learning because they need big data. But just last year, the beginning last year, I was in Hangzhou, in Zhejiang University. Zhejiang Lab, okay, in Zhejiang Lab. So doing that, I read, carefully, go through this paper. This paper they call PINN. It's published in 2019. Okay, especially this article. So this article is a review article in 2021. Then they said, okay, if your data is small, you have a lot of physics. Okay, if your data is bigger, no physics. Okay, no matter what you're doing, so you may have this a copy from this paper. So you have observation bias, you have inductive bias, learning bias. So, but the nature, the materials, they have to satisfy their intrinsic features. Okay, they have their symmetry, they have to follow conservation laws, they have their dynamics. So how to do that? Through PINN. So now I write the second book. I'm writing, still working on it. The second book, I ask my student to plot that. They have one we call for forward problem. Okay, this you solve your partial differential equation. You are not use your WASP, your or other molecular dynamic simulation, or your fundamental. What you use is a neural network. You use a neural network to solve it. Then you put those governing equation, boundary condition, initial condition as a loss function. Everything you put as a loss function. Then you can check, put a criteria there to say whether you are satisfied to this loss. If you are satisfied this, then this neural network is your solution of those partial differential equations. The partial differential equation may not be only one. It could be, a couple. Or they are coupling, a set of partial differential equations. As we use that in physics field simulation. Okay. So this is not a big deal, okay? It's just a train after you. The key issue, after you train that, you have your experiment. Okay? Then what's the advantage? The advantage, you solve this partial differential equation or equations. You can generate a lot of data. So you don't need to worry about, I don't have enough data. Okay, you can generate as many data as you want. Okay? So then your experiment, you have just a very small data. For the inverse, then you put your wire trained this, you can find what's that is a parameters you used in your, they satisfy your experiment data. Okay, or maybe some partial differential equation, you want to modify it a little bit, and so on. You can do a lot of things. Okay, your home university, okay, Brown University, those is a PIN proposed by those professors there. So now they get a bigger grant from the U.S. government. Okay, there is a U.S. put a great offer. Okay, they are trying to continue develop this. Okay, this. In materials community, I said it's better to do active learning. Active learning is actually we call adaptive material mechanics innovation. I call that. So you have to use your domain knowledge. I put the domain knowledge as a harbor. Okay. So no matter if your data could be purely computation data, could be experimental data. I personally like experiment data more. Okay. I prefer experimental data. So you have your data. Now from those data, initial data you build up here I call it a database. Magneto is so big, you call it a data set. It's more relevant. Then you analyze use data. We do a data pre-processing. Then we develop a machine learning model. Then we evaluate our model. Then based on this model, I use the Bayes global optimization, okay, to determine what's the next experiment I should do? What is the next computation I should do? I want to reach my goal. Okay, then you have used that. Okay, the reason is all those models, they have some uncertainty. Experiment have uncertainty. Computation also have uncertainty. Okay, the uncertainty that is in AI. If you are a student, then your supervisor will ask you, or you repeat your experiment to get your error bar. You have to use your error bar. You cannot just done once, and that's the result. That's it. Okay, you have to repeat. Okay, so once those is to handle this uncertainty, then you have to balance. I call exploration, exploitation. Okay, you have to balance this. But domain knowledge is very, very important. Okay, emphasize that again. Now this is one former work. Done at Hong Kong USD. I think it's at the CTO. You have this advanced facility, correct? We call the STM. Okay, that is the more advanced TM. The TM is scanning TM. Okay, so there I show you if I scanning the same sample horizontally and vertically, and supposed to get the same results at that is atomic revolution, but unfortunately they are not exactly the same. Unfortunately, okay. So then they have noise, they have uncertainty. So in this is a paper, we develop a method to correct the noise, the noise in STM. How to convince reader? How they know your correction is correct? Okay, I can do that. I do simulation. The reason is the truth from experiment. You really don't know where is the truth. You just try, okay, try your best. So, but in simulation, I can think, if I don't put a noise there, I assuming the simulation results is the ground truth. Then I put a noise there on purpose. I make the noise very big. Then I use the method to correct, to go back. Okay, so through this, we are trying to convince reader those is a method we proposed works. Okay, that's the purpose. So now, philosophically, we are from data we gain knowledge. I have mentioned that. Now people talk about the machine learning, okay, machine learning. So when you gain is knowledge, what can you do? Further do explanation, because planning is what's going on to you say understand. Then we can do a prediction, okay, predict. More very hard is one you can do control. So that's AI lab, we need this, control. Okay, we are use that like you say we are in AI lab. Okay. So here I put that from the website. I found this one. I don't know. It's really this. It looks like this. This is a Newton's is a picture. Okay, I said that learning can be done by individual human being. Okay, especially if those is famous people. Okay, by you use your brain. Okay, to learn. But nowadays you should also put a machine learning there. Okay, you put a machine. So I put the sentence. I said the development of nature science is the continuous, endless progress that a human being observe nature behavior and develop a learning model, then gain knowledge. Okay, that's it. Never finished. Never finished. Always is going on. Okay. So here I take two examples, very popular to all do mechanical property of materials. Okay. First is Paris law for fatigue cracking growth. This comes from data. Now, so far, to my knowledge, we have not found a theoretical derivation, a model. We always use that. Okay, we use that. So this one is very, very important. The reason is most of the failure to materials, to structure, is by fatigue. Most of the failure, okay? So another, the area is the cities area. You are working on metal. Okay, I'm joking to those people working on metal, okay, metals alloys, although Yuntian is working on this. So the mechanical property, okay, except creep resistance, most of the mechanical property will get improved if their grain size gets smaller. Okay, yeah, the small. Of course, if this grain size is smaller than a critical size, they have an inverse hard pitch equation. No, we are not talking. To industrial application, we never reach those small one. Okay, to academic research, you can. Now, those is a hard pitch equation is get from data. Okay, it's get from data. Now later on, in last century, we have developed a dislocation theory. So based on dislocation theory, we can derive, we build up some model, then we derive a hard pitch equation. Very, very interesting. Not only one theoretical model, you can use a different theoretical model to get the same equation. Okay, so that's just very, to emphasize that, how important the data play. Now, I strongly suggest you, we want to combine both. Why I call it knowledge-based and data-driven, put them together to find a formula, to discover equations. Okay, I want to make a balance. Not it's just data-driven, and also expert. Okay, I think it's Ken just mentioned that you found a very important equation. Okay, we are to learn more about your equation. Okay, that's an expert. Okay, get that equation. So we want to combine them. Okay, we want to combine. So now, just very briefly talk about this machine learning. Okay, the error is analysis in machine learning. Error have those basically, we can separate some to the intrinsic error and the bias, the variance. So the philosophy is somehow different. In my whole life, I derive an equation. I always trust that my equation is correct. Because in some sense, I said, okay, if you are an experiment and not fit my equation, must be something wrong with your experiment. Okay. In data-driven is not that. They said that you cannot find the true equation, true function. Only you can find from the approximate, say, function or equation. There are so many approximate functions. So when I was a PhD student, with my supervisor, or CT have excellent work on there. We did say hydrogen embrittlement. Okay, so at that time we argued to each other. Over the world, have different mechanisms. Okay, we have one. Say, so then people argue to each other. So that means each of those mechanisms is actually approximate is a formula. Okay, it's a property. So now you can find say AI try find from those all the possible, okay, approximately say solution, found the best one. So that's AI. So you do say error analysis, you will find that they have a bias, another is a variance. So they have a bias variance dilemma. So I will show that in the next PPT. So now to get there, the intrinsic one you cannot change. Okay, usually I put one example, stock market. You want to make money. Okay, but the stock market, their intrinsic error is very big. So to most of people, we cannot make money. It's difficult. Okay, but the AI can do to try to put this to a bias and the variance, try to put them together to minimize it. Okay. Then you related to two critical issues in machine learning. One is feature. Okay. Another is your search space. You want to search and which space you want to search. Okay. These two are very, very important. So here I just mentioned. So for this I copy from famous textbook. So if to this side, if your model is very simple, small data, okay, simple, so you have a high bias, just like you see we are do. Your data is small, you bias your. Then there is have a low variance, okay, high bias, low variance. But to this side, you have low bias, high variance. If you use just training your data, okay, then on the side to testing your data into two subsets. Then during training, your model will get a prediction, get better. So usually we call this is overfitting. So the best one is to use their testing, okay, at this part. So this is there is the major difficulty I have mentioned. To materials scientists, our data is small. We are not big data. Okay, we are small data. That's why I like a PNN. We use some of our domain knowledge, okay, generate, solve some partial differential equations or some famous very accepted formulas, okay, to generate more data. Another, the influence, okay, those influence factors too large. Mathematically, we said they are in high dimension, high mathematical dimension. Okay. The third, they have some uncertainty. Your data scatter greatly. We also know for brittle is a fracture. Then in theory, it's very easy to use a purely elastic one. But experimentally, they have greater scattering your data. Okay, you have to keep that in mind. So, and also another challenge is the model, AI model is not unique. You can generate a lot of different AI models. Okay, you can generate. Now, when I talk about this, some of my friends talked to me, said, "Oh, Tongyi, so we are theoretician. We derive our model. Once we have a model, our solution is unique." Now, my answer is no, not that case. Okay, I'll give you two examples. So this is when I'm working at the Hong Kong UST, I deposit a thin film on silicon substrate, because I always say we are trying to do something for microelectronics, okay? We are trying very hard. So now, when you deposit thin film, you always have a residual stress. So my idea is whether I can do an indentation testing, generate some, say, a crack, then measure the cracking length. I can estimate how large is the residual stress. No matter your thin film is crystalline thin film or amorphous thin film, doesn't matter. Once the only things we need, we can generate some, say, indentation crack. Okay, that's his idea. Then I'm working on fracture mechanics. Okay, so I derive one equation, I put it there. So now we found these two famous scientists. I also know them. City whether you know. Law is in NIST, okay, working. It's also is 美国工研院. Okay, yeah, they are very, very famous. Also working in the same area. They propose another equation. They propose this equation. You can see if you treat this as y, then c square root c as x. You can see this is linear proportional to x. But this is inversely, say, a linear proportional to x. I cannot control it so well. Okay, this is a non-inversely. Okay, you can see that the two equations looks are totally different. So I ask my student use the same experimental data to fit these two equations. Then from the fitting, you cannot tell which equation is better. You don't know. Okay, so due to experimental errors, a data set can be fit by different equations with more or less the same goodness of fitting. Okay, with more or less the same goodness of fitting. So that is one example. Another example. Okay, this the further work is by our two famous professors, Professor Bill Nix and also Professor Hua Jiangao. Okay, they proposed they are based on geometry necessary dislocation, and they say a random distributed dislocation. Based on this, then they develop a size-dependent hardness. Size depends on your depth. Okay, you do an indentation. Okay, then they develop this equation. Then some of my friends talk to me. They say, well, at that time it's a very hard research topic. People say, oh, Tongyi, you are so good, you should do something. And I think, oh, what can I do? So I basically on apparent surface stress, I build up another model. It's the model assumption starting point are different. Then I derive another equation. So this equation derived by me. Okay. So I asked my former student, Xu Weihua, okay, to collect all available data. Even though we actually have more data, I just show you the 4 data. Okay. I use two different equations to fit it. Then 2 different equations, they get more or less the same goodness of fitting. So you don't know which one is better. Okay. So now this is a new work, just published, except I have not really, probably online, you see, today or tomorrow. Okay, we just accept. So what are we doing that? Handle small data. So how many data? 47 is very small. Okay, very small data. Even 47, but their dimension very high, even though only composition. So you think about the composition here, I have 7 available alloy elements. This one the server, I fix it. Okay, copper fix. I still have slew. Okay, so now from there, those is we want to get a high strength and high elongation. Can we develop some new lead-free solder? Okay, that is it. Kian, you are the expert. Okay. So this one, because we're working with Yunnan-Xi, it's a bigger project. Okay, they support it by Yunnan-Xi. Okay, now I develop a new software. Okay, new algorithm. I basically modify. Some available one I modify. I give a name. I call this is a software. It's a tree classifier for Gaussian processing regulation. Okay, so we get this. Then use this one. We separate them in 3 even smaller subset. The original is 47. Now I get is even smaller. Okay, only few. Okay, then. Now what's the advantage? The advantage original your search space is larger. Then after I see separate those, each search space becomes smaller. Then I can develop some model to get very good. Then use my domain knowledge. My domain knowledge is you have ultimate tensor strings, you have elongation, and multiply them together. Then they become, say, 2 objects become 1 object. Then become single object search. And this Y also approximately standard for the mechanical work, okay, per unit volume observed by your tested sample. They have physical meaning. Okay, keep that in mind. So now we have, so for each time we repeat, we use that, we can find a new, okay, that is a prediction. We use the 3 sites, each site we get a new one. Then I use how to accommodate, I mentioned that we use Bayes global optimization. They have a different algorithms. I use 2 algorithms to do this. Then for each algorithm, I have asked a student to repeat a couple times for the repeat. Okay, now I can get an error bar, everything. Okay, then I found a new error, 3 new errors. Okay, lead-free. Now we are do active learning. This is initial work. Now we even get better, much better. Okay, so now of course, materials people always do characterization to explaining what's the mechanism, why they are caused this, make a story. Okay, so I think I say how to make a story is my focus, today's focus. Okay, I can make a story also. Okay, but my purpose will get a new. Okay, we can put on the market. Okay, something new. So now talk about the small data. Small data, I separate small data in 2 parts. One I call is unreliable, and one we call is reliable. For reliable data, we do have a lot of a method. We can do a data augmentation. We can do transfer learning. Actually, PINN for inverse is a problem. It's basically a transfer learning. Okay, you have to understand that. It's basic. Okay, now if they are unreliable, what's going on? Okay, if they are unreliable, in my personal view, use your domain knowledge. Okay, use your domain knowledge. So use the domain knowledge, this one, I first gave the presentation about this work just a few years ago at Singapore. We celebrate the fracture mechanics 100 or so. Okay, so Professor Batat out there. Okay, so that's why I use his data. So that's why this data have sample size. The big one is this big. This is a small one. I have 4 different sample size. In addition, they have notch length. those notch lengths, the depth of notch, they are also different. Okay, and you have a size, sample size dependent phenomena, and also notches say length dependent phenomena. Okay, so I analyzed their data, found that their data are not reliable. When I gave this prestige talk about this, Professor Bajat was not very happy. Okay. Anyway, his is the largest data. They are published in the literature that have more groups do the similar research. Their data size is even smaller than his. Okay. Now, what can I do? Okay, I make it two common. Everybody can accept the domain knowledge. One is here. The probability of a bigger defect existing in a large sample should be higher than that in a small sample. Everybody accepts that. Okay. So another is everybody accepts that the deeper the pre-notch should induce a higher stress concentration at the notch tip than a shallow pre-notch. Nobody argues with this. Okay. Based on this, I put 4 hypotheses. And based on the 4 hypotheses, I put the further size-dependent normal distribution. In Singapore, I gave a talk. It's talk about this. I use the Weber distribution. And later on, I said the Weber may not be good for 3-point banding. Then I changed it to normal. Okay. Then you talk about those size and the pre-notch. I put another normal distribution model. So what's the advantage? The advantage is because the data is small, so we cannot see from those data, we cannot identify each individual distribution. Okay, for that. So now we are trying to use all the data to determine each of these distribution. That's the purpose. We have to find the distribution. Why you have to find the distribution? Okay, I think the reason is we are talking about the safety of your structure. We have to make this failure probability as small as possible. Okay, I can stop that. Okay, yeah, okay, as small as possible. So, but you do experiment, although you observe is a mean value. Most of those values are along this mean. You cannot find those small probabilities sample. You cannot observe them. That's a problem. So once you use that, you have a distribution, then you can do. Okay, that's no problem. So then we get from there, we can get that's from their data. We can see when they are biggest data, then they have no side effect. Seems. That only depends on the pre-notch, okay, the depth of pre-notch. Once it depends on this, fracture mechanics come in. Okay, I can calculate the stress intensity factor. Okay, then I put this, they call this a fracture processing room. In metal, we call that is a plastic deformation room in front of cracking tip. Okay, then we can put it there. Once we put it there, then we can get this K1C and also the fracture processing room size. Then those two values, we can find this in the literature. Everybody accepted that. Have no argument. Okay. In terms of my time I use all my time. So I will not continue my presentation. If some of you interested, you're welcome to discuss with me. Okay. Any questions? Okay. I have to go very, very fast. I will not talk about this. Okay.
So if you have a question in front of you, this is a button. You press the button, then the speaker will come up. You can ask a question. Any question from the audience? Yes.
Thank you for this insightful presentation. So to run a reliable machine learning tool, we need to consider both successful and failed data. So, but today, most of the journals only publish successful data. So how to deal with the scarce availability of failed data?
Okay, a very good question. former presentation, I have one of the PPT talk about the failure data, okay? So if in materials processing, we want to find at which processing condition you can make your sample, okay? So you want to find the boundary between successful and failed one, correct? You want to find the right boundary, you need failed data. That is actually one Nature paper, okay? Very, very important, okay? Without those failed data, you cannot find the boundary. From data science point of view, there's no success and failure, okay? But your data must be reliable. Okay, if you get unreliable data, you repeat that, you cannot repeat it, then that's a problem.
Any other question?
Professor Zhang, excellent talk on material mechanics interaction. My question is this. In your talk, there's no time as a variable.
Very good question.
Now, wait, let me finish. For example, on consumer electronic product,
Yes.
then when you buy this cell phone, initially, no problem, doing very well. On the other hand, as you use like 3, 4, 5 years ago, later on, it may fail because electrical conduction generally heat, cause phase change, so there's a so-called mean time to failure. We like to know that, particularly for
No problem,
industry.
no problem. Very good question. Okay, I just mentioned that if you talk about, say, fatigue failure, talk about the creep failure, that always relate to time, correct? Okay, so now I have my student, actually we published one paper already, I did not put it there. We use AI to predict battery, lithium-ion batteries is life. Yeah, that is highly depends on time, correct? Or we can also handle, you see, those waves. The waves are always with time, correct? No problem. Very good question, but my time is limited. You want to, say, discuss more, or you can discuss more?
No doubt materials, electrical property,
We do.
other mechanical property.
No. We get, you see, one challenge, for example, Professor Liu Yi from Shanghai University, we get, you see, one, he's doing some project. Now, they come to me, okay, they ask me for help. They want to get a high strength and a high ductility copper alloy, electric copper, correct? So how do you do that?
How do you do that?
How do you do that? So this afternoon, Professor Liu Yi, I don't know whether around you give a presentation. He also developed he calls it a very good feature. They call it the central environment features. It's a very good one. I like that. Okay. So I always ask.
Naturally, you need to use mean time to failure equation.
That's correct. I just say I'm working on it. I developed because I know I derive equations. I derived a new equation. Want to get this for hot pressure, okay, for high temperature alloys. Hot pressure, how do they have a working hardening? They also have a working softening as well. It's not very easy. Okay, I get one equation.
Any other question? Yeah. 推荐。张乐 this
我
this
那
side.
个就用中文了，因为我对，因为我是那个上海大学毕业的，材料学院的。因为我毕业的时候，就是这个基因这个课还没开，所以说呢，就是说我在上海大学待了5年，感觉很遗憾，就是说有一课一直没上。然后今天就是借着这个机会，终于把这一课补上了。 然后呢，就是我知道在座的有很多人做这个高商的，还有做易购的。我在想，就是说我们这个基因工程，就是说怎么在这方面，就是说给一些对指导。
So, as I mentioned, this is research culture. Okay, I call it a culture. Okay, so you have to change. You cannot say every time I do experiment, I use my brain. Of course, that's very good, but they need smart people like you guys. Because some people are not so smart. We have AI. Okay, we use the AI to learning what you have done. Then we're teaching to our young students, young faculty members like them, and they can learn. Okay, that is the power is a new try. No matter I mentioned that, you have your original, you have your approach, your methodology. But I ask you to pick a new tool. The new tool is AI machine learning.
Any other question? I'll have maybe I will ask the last question. It seems to me that AI is very good to optimize the properties like strength, ductility, or the toughness. But if you want to study for some new physics, try to find out what's going on, it seems it is more difficult. That's my feeling. Anyway.
They have a new actually. They have some specialist a group of algorithm AI. They call the recurrent neural network, and also some we call it a long short term memory algorithm neural network. Now recently a new one they call transformer from based on transformer, they develop another informer. Okay, that's very, very good. Everything related to time. Okay, informer is a brand new one. Algorithm.
Time reason, let's thank Professor Zhang again for the great talk. Okay, this afternoon we will have the workshop continuing at 2 p.m. If you are interested, we'll have more talks here. Thank you, everyone.